All right, let's discuss the 11.6 WebAssign on the ratio and the root test. Ratio test is one of the most important series tests of all, and I think that's why we've got a bunch of exercises here. So we'll take it bite by bite. Right, what can you say about a series sum a sum n in the following cases? Well, essentially in this first case here, we are saying that we have similarity to a geometric series with common ratio 7. Well, that would give us divergence there, because remember, when you talk about geometric series and their convergence, common ratio less or equal to 1, or excuse me, less than 1 is our criteria. Greater than or equal to 1 would be divergent. As it turns out in the case of the ratio test, because we're taking a limit and because we have sort of imperfection in the result, when we get down here, we would have a can't be determined result. What about here? What if the ratio of an over an, excuse me, an plus 1 over an, as n goes to infinity, limits to be 0.2? Well, this is drawing analogous comparison to a geometric series with common ratio 0.2 or 1/5, which is less than 1 in absolute value. And we would get absolute convergence in this case, absolute because of the absolute values on our consideration. You can do the ratio test without the absolute values, but that's just not something that we're going to focus on. And so, right, what about this last case? When the limit associated with the ratio test, namely an plus 1 over an, evaluates to be 1, this is a case where we actually could converge or could not converge depending upon the circumstances. And so nothing can be determined in this case. Right. Now, normally, whenever we are employing the ratio test, it is because we have like an exponential expression, something with an n upstairs, that sort of feels like a geometric series. And so because we've got that exponential expression, the ratio test may work well. Because if we don't have a geometric series here, if you write out the terms, that n squared downstairs is sort of ruining a geometric series from appearing. And yet, when we evaluate our limit here, what you will find is that that minus 4 to the n upstairs is going to dominate the n squareds whenever you're taking the limit. When you're taking the expression of an plus 1 over an and looking at the limit as n goes to infinity, the n plus 1 squared and the n squared on opposite sides of the fraction bar is just degree 2 polynomial over degree 2 polynomial equal heavy. That would limit to 1, whereas the minus 4 to the n over minus 4 to the n plus 1 will limit to be minus 4, absolute value of minus 4. So you'll see how that plays out here. If the extra power of minus 4 is downstairs, you get convergence because you'd have 1 over minus 4, 1/4 is your absolute value coming out. On the other hand, if the minus 4 is upstairs, which I think is how it's going to play out, you'll end up with this limit evaluating to be 4, which would give you divergence. What about this next one? Again, we think ratio test here because we see these exponential expressions. We've got a minus 1 to an exponent, a 7 to an exponent, 6 to an exponent. The n cubed is going to ruin this from being a geometric series, and yet it's not going to have an influence whenever we take our limit as n goes to infinity. There's going to be a lot of factors here to parse whenever you're looking at this limit. But one thing you can do immediately is know the factor of minus 1 are going to just nullify because a factor of minus 1 and an absolute value would just be 1, and that's going to be negligible. And so really we can just focus on the 7 to the n's, the 6 to the n's, and the n cubes. And I think because we've got a 7 upstairs and a 6 downstairs, we're going to be drawing comparison to a geometric series common ratio of 7/6. 7/6 greater than 1, I think we get divergence in this case. The next one here, factorials. Factorials are another tell or another indication to consider the ratio test because factorials work beautifully with the expression for the ratio test. K plus 1 factorial divided by k factorial is just k plus 1 because k plus 1 factorial will also include k and every number less in its expression and would cancel with the k factorial perfectly. So here my suspicion is because we got the k factorial downstairs, the terms of this series are going to 0 extremely rapidly, and I'm going to guess that we get convergence. In fact, I think we're going to draw a comparison to a geometric series with common ratio 0. The terms get so small so fast, which is definitely going to give us convergence because any ratio here less than 1 popping out of this limit would be an indication of convergence. Next, k e to the minus k. It's probably easiest here to write the e to the minus k downstairs as e to the k. And if you do, you have that exponential term. Remember the base of e is what, like about 2.7. So essentially we have 8k over about 2.7 to the k downstairs. And because we have an exponential term at all, because the k is showing up in the exponent, that's a tell that ratio test could come into play. Incidentally, the 8k that's upstairs, I think, is going to cancel out whenever, I know, in fact, whenever you apply a limit, but then, dealing with the e to the k, that is going to dominate the expression, I believe, because the e is downstairs and it's a 2.7 downstairs. I think the limit's going to pop out here to be 1 over e, if I'm not mistaken. And well, hey, 1 over e is going to be less than 1, and that's going to give us convergence here. This next example, hey, we got both the tells of a ratio test here. We've got both the exponent, the 89 to the n, and the n factorial. So this is a sort of custom made for the ratio test, if you will. Now, as it turns out, I believe the n factorial is going to dominate the 89 to the n, because whenever you play out the limit, you get an 89 popping out from the exponent, and then you get an n plus 1 popping out from the factorial. And as n goes to infinity, n plus 1 is going to crush 89 wherever that 89 is. So play it out using the step-by-step of the tutorial, but I think you'll get divergence in this case, because I believe the limit associated with the ratio test is infinity, meaning that this series is like a geometric series with common ratio infinity, which is, disastrously divergent in some sense. What about this next one? Again, we've got pi to the n, minus 4 to the n minus 1, these exponential terms. When you got these exponential factors within your expression of your series, that's a tell that the ratio test is coming into play. And in fact, it does here. The n is not an exponential term. That's the only thing that's going to be sort of preventing this from being a geometric series. But yeah, when you got the pi upstairs and the minus 4 downstairs, when you play out all of the numbers here, I believe what's going to happen is we'll get this limit being pi over 4. And pi over 4, you got to process for a second what the value of that is. Pi is a little bit more than 3. Divide that by 4. I think you'll end up with a limit here associated with the ratio test less than 1, which is drawing comparison to a geometric series with common ratio less than 1 in absolute value. So we're going to get absolute convergence. Right, this next one, this is a classic example. It's a great exercise, and you're just going to want to have to write out all the bits here. I mean, upstairs you're multiplying. You're multiplying multiples of 8, and then downstairs you're sort of multiplying successive multiples of 1, like 1, 2, 3, 4, 5, 6, all the way to 10. And so if you think about how that should play out, you should be able to cancel a lot of what's upstairs with a lot of what's downstairs and just get a bunch of factors of 8 left over. And that's going to play into your evaluation of your limit. So here's one, just trust the process, write out what you get when you plug in n plus 1, write out what you get when you plug in n, divide them. The bits with the factors of 8 are going to cancel out nicely. The bits with the n factorial are going to cancel out nicely, and you'll get what you get. And I think, I could be wrong, but I think this one diverges. We'll have to play it out. Okay, now we're getting into the root test territory, because anytime you see sort of a functional expression raised to the nth power, the root test is just going to kill that n straight away. It's going to neutralize that n, and that's going to be sort of good for business. Then we can just focus on the absolute value of what's inside, which in this case would limit as n goes to infinity to 1/3. And so here we're going to draw a comparison to a geometric series with common ratio 1/3. So the root test is just a different lens through which to draw comparison to a geometric series, but it's particularly effective when we have these series with something raised to the nth power, or even something raised to the 5n power. Because once you cancel the n away, the 5th power will still remain in your limit, and yet you'll just have sort of, in this case, -2, the ratio of the dominant coefficients equal rational function, -2 to the 5th. Whatever -2 to the 5th comes out to be in absolute value, that's going to be what, like 32 or something. So hey, this series is sort of like a geometric series of common ratio 32, which would diverge. Right, again, root test here, because you've got that factor of k, and this one's going to limit out to be 1, unfortunately, which the root test is blind to, so we would get inconclusive here. If we wanted to determine the convergence or divergence of this series, more series tests than the root test would be required. I don't think the ratio test would work either on this. This is just sort of a funky one that would require more work. Okay, determine whether true or false. If the series converges if this is less than 1, yeah, that's true. If this thing is less than 1, then the series converges. In fact, it converges absolutely, but converging absolutely means you converge without the absolute being explicitly articulated. So, right, this is definitely true. What about the next one? Use any series test term, blah, blah. Okay, right. So this is going to use your root test, because you got that factor of n up in the exponent. And then you're essentially limiting the absolute value of 2n over ln, which that's infinity over infinity, but then you can use L'Hopital. So after you use L'Hopital, I think you will get this to limit to, gosh, I have to play that. I think you get infinity in this case because the 2n should grow a lot faster than the ln. And then essentially you're drawing comparison between this series and a geometric series with common ratio infinity, definitely divergent here, the way that shakes out. Determine whether the ratio test is inconclusive, conclusive, or conclusive convergent, or conclusive divergent. Well, take this first example. There's no exponents or factorials here to help you out. Whenever you play this out, I believe the limit associated with the ratio test comes out to be 1, which would be inclusive. What about this one? Hey, you do have that 7 to the end, so the exponential term should be to your favor here. Because it's in the denominator, I think you'll get your limit associated with your ratio test to be 1/7. So that'll play out as it might. Here, the square root n is going to be negligible. That's essentially like a polynomial term, but not exactly. It's just a power term, n to the 1/2. Well, that's going to, the power terms are going to negate each other, neutralize each other whenever you're computing the ratio associated with the limit associated with the ratio test. Then that -4 that's upstairs is going to tell the story. I think the limit associated with the ratio test is going to come out to be 4, which is going to give you a conclusive result. And here, similar to what we had in A, although in a more convoluted example, I want to think of this, limit comparison test would be preferred, honestly, limit comparing to 1 over n to the 1.5. But as it is written here, it is what it is. The square root n's are going to neutralize each other in the limit associated with the ratio test, and the 1 plus n squared are going to neutralize each other. You're just going to get 1, and that'll be inconclusive as a result. This series diverged. Well, you'd have to run the ratio test to be sure, but I'm pretty sure this one converges, and that's because while the n is negligible here, the 2 to the n is non-negligible. That's exponential. That's going to play well with the ratio test, and because the factor of 2 is downstairs, I think the limit associated with the ratio test will give a half, but you'll have to run the numbers to be sure. The ratio test can be used to determine whether this converges. That is false, because the ratio test is going to be blind to this series. Polynomial terms just get neutralized by the ratio within the ratio test whenever you take n and let it go to infinity. So you essentially get n to the 9th over n to the 9th plus the leading coefficients. It'll be 1 over 1. 1 over 1 is 1, and that's where the ratio test is undetermined. Here, factorials work beautifully. In fact, factorials get gigantic really quick. And so 1 over n cubed is definitely going to converge, and the ratio test will, in fact, tell you that. I think the comparison here is going to be drawn, if you run the ratio test, the limit that pops out is going to be drawing a comparison to a geometric series with common ratio 0, which is like practically nothing, right? Okay, whoa. An is greater than 0, and this limit is less than 1. How in the world is that possible? How in the world is that possible? Oh, less than 1. Okay, yeah. I was thinking less than -1. I don't know what I was thinking. Oh gosh, look at this. So see, if the ANs are greater than 0, then you might as well be thinking of this in absolute values, because the absolute value of this would be just the same as what it is. And so the limit of this being less than 1, the limit is really the limit associated with the ratio test, because you could park absolute values and get the same thing by virtue of the fact that the ANs are positive. And so what you know here is you have a convergent series. You know the ANs are convergent via the ratio test. But since the ANs are convergent, like all convergent series, the terms go to 0, right? The fact that the terms go to 0 don't necessarily mean that you have convergence. But if you do have convergence, you know the terms go to 0, and that's exactly what we have here. So we'll stop this here, and that'll be that.